Well, it's my pleasure to introduce this morning's speaker. This is the Eagleson Lecture, and this morning it'll be Ying Reinfelder. Ying comes to us from the Department of Earth and Planetary Sciences at Rutgers University, and a few of the research topics that she's worked on are highly relevant for this meeting, and this is why we've chosen her to be this year's speaker. Some of these topics include the role of groundwater in the global water cycle, climate and ecosystem dynamics, the Earth's hydrologic cycle in the past, the role of groundwater in supporting Amazon's seasonal evapotranspiration and precipitation recycling, regional hydrologic and climatic impact of large-scale groundwater pumping for irrigation in the U.S. High Plains, the future of freshwater resources, global groundwater database in support of Earth system modeling, the community initiative to develop a digital representation of the Earth's crust for simulating subsurface fluid flow in the Earth system models, and the role of fractures and sedimentary rocks in controlling groundwater flow and groundwater river exchange. These are just a few of the topics that Ying works on, and the reason that she well exemplifies the theme of this meeting. With that, I welcome Ying to the stage as this year's Eagleson Lecturer.
Thank you, Brian, and thank you for the organizing committee to invite me here. I'm really honored, and I'm really standing here humbled. The title of my is very on the top. The title of my talk, Groundwater in the Critical Zone from Column to Planet, is ridiculously broad. Sorry. Okay. So the title of my my talk is very, very broad, not because I'm able to speak to such a broad subject. It really reflects my desperate attempt to speak directly to the theme of this biennial meeting. But I will only be able to use a few examples and make a few points. And so I'm going to focus on shallow groundwater and ask the following question. Is groundwater, as we know it, as we hydrologists know it, at the column and hill slope and watershed scales, relevant to understanding patterns and processes at very large global scales? And in particular, does the intimate groundwater surface water interactions, the rise and fall of the water table, the downhill convergence through macropores, etc., and the constant exchange of surface water and groundwater, does this common sense, what I call, that we rely on to explain everything we observe at this scale of observation, are they also essential for explaining planetary scale, large river basin scale processes? So that's the question, and it's kind of a strenuous question, I understand, but I arrived at this question in a very strenuous way. I took many years off raising my children, so when I returned to work about 10 years ago, I asked myself, what problem should I work on now? So I started reading, and how to forward? Naturally, global environmental change floated to the top of, at least in my mind, as the most important problem today. And so we have come to understand that we are indeed conducting a planetary scale experiment that the Earth probably had not seen before, the speed of carbon cycle acceleration. And we have launched GRACE, when I was gone, not paying attention, and we can actually observe the seasonal loading, unloading of the water on land and the secular trends. And we have launched MODIS, so we can actually quantify to great resolution, 200 meters or so, of the primary production for the entire planet. And this gives us a new perspective. And also, we're compelled to ask a new set of questions. For example, how would the water cycle respond to and regulate the climate and ecosystem change, a few hundred years down the road? And how did it do all these functions in the past thousands and millions of years at these very critical junctions of the Earth system? So these are the questions that we are compelled to ask. And then to answer this planetary scale questions, of course, we need planetary scale tools. And one of the best tools we have is the Earth system model. And on the top is the, can you do the top first?
Mic, if that would be easier,
yeah.
And that way people might be able to hear a little bit better.
Okay, how do I do that?
I think use talking method or something to get it done.
All right. Is this better? Okay. So it stopped. On the top is the NCAR simulation of atmospheric water movement. And you see the white water vapor rises from the surface and rains out in those orange blobs. And on the bottom is a very high resolution eddy resolving simulation, a global scale of water moving in the ocean. And I find these really awe-inspiring. Just despite the problems we have with our GCMs, just to think that we are able to, based on the field conservation laws and some empirical equations, to set the atmosphere in motion and to set the ocean in motion. And just to think that we are actually able to build a crystal ball and gaze into it, how fuzzy it is, and possibly see the future trajectories of this planet as well as the past. And then there's this question, where is water on land? And the atmosphere is alive, the ocean is alive, but what happens to the water on land? And as hydrologists, we have some idea. It sort of converges to low ground, from high to low, and in multiple scales, it's kind of slow compared to the atmosphere and the ocean. And so how does what we know, the convergence of groundwater and the slow motion represented? How are they represented in those magnificent models? And so I put this question to my then office mate, Gonzalo, who was a climate modeler, and learned that in these models, land are very large slabs, and rain falls through. Some gets retained by the soil, and then marched through the ocean through directional flow direction files such as this. And I asked, where is the groundwater? And he said, what groundwater? And by missing groundwater, the implication is that land drains freely, and we quickly get rid of the water. And that also means that the ecosystems are rain-fed only. And as a hydrologist, trained as a hydrologist, I can't make sense of anything I observe without considering groundwater part of the system. But how do climate models interpret what they simulate without the groundwater? How do they make sense of that? And so I set out to answer why. Why does such sophisticated Earth system models with dynamic vegetation, with biogeochemical cycling, have such simplistic water cycle, which is really the most basic of all the cycles on Earth? And there are very good reasons. For example, our Earth system models today really came from GCMs, and which came from numerical weather prediction models, which are short-range and atmospheric focused. And the land and ocean were brought in to improve atmospheric predictions, and the grid has to be large, the process has to be simple. So these are some very good reasons. And the code of land, the conceptualization and coding of land processes are done by climate scientists. And so these are some good reasons that why the hydrology is so simple. And perhaps there is a more important reason. That is what we know as true, as we hold dear and near to our heart, the hill slope, the column hill slope, and the watershed processes are just not important. They just cancel out. When we zoom out, we just don't see that. Maybe that is the reason. After all, our notion of the water distribution on land and our biome distribution on land are all very much guided by the large-scale climate patterns. And also, we haven't seen a groundwater table, and so it cannot be important, right? So that's my question for the last 10 years. Is groundwater relevant to global processes, the way we understand it? And so I'm going to show, I keep pushing the wrong button. I'm going to show some of my results of compilation and synthesis of observations and some conceptual models, and where, I have these buttons that confuses me. And where possible, I'll use some numerical models. So which will also be the question of this talk, for the rest of this talk. Of course, the first question is, how deep is the groundwater? We have never seen a global map of groundwater. And if it's deep, then land will drain freely, and the vegetation will be rain-fed only, and all my problems will go away, and end the story. So I set out to compile groundwater. I spent many years, and with the help of many colleagues around the world, and I came up with this map, which is not much to look at. There's more data gap than data. But I think there's still something we can see. I'm going to zoom into North America, which has the most data. The first thing we see, of course, is the signal for groundwater depletion. All the colorful patches show up as orange patches on this map. But I'm not going to focus on this because I'm going to cling to the natural signal and savor the natural world before it all disappears. And so what is the natural signal we see here? I really see a very weak climate signal. You see shallow groundwater in the arid regions as well as in the humid regions, cold regions as well as in warmer regions. And you really see a very strong topographic control, as we expect. Nothing new here. And we see rivers, valleys are shallow, and the lake basins are shallow. So topography really played a very important role in reorganizing the climate input, and it sort of erased the climate signal. And then we also see the sea level control, because shallow groundwater is found along all coastlines, just because land drainage cannot go below the sea level. That's our boundary condition. And to put that into a conceptual model, we can let the land relax, rain falls on it, let topography reorganize the water, and then use sea level as boundary condition. Then we can expect those are the places the shallow groundwater ought to be seen. Along the coastline, in the river valleys, lateral convergence, and it sort of transcends the climate. So that it doesn't matter even in humid and arid climate, you'll have deep groundwater, shallow groundwater. And in very arid climate, you can still have very shallow groundwater as long as you have a large enough drainage area. And it's going to pop out sooner or later. And those are the spatial patterns that really don't correspond to climate signals very directly. And then we all know that groundwater is kind of delayed and dampened, so it's often out of phase with rain, and it's more stable than rain. Putting all this together, we see that the groundwater patterns and timescales have some level of decoupling from climate. This gave us a good reason to ask the next questions. Can groundwater patterns and processes explain large-scale patterns and processes that are not explainable by climate alone? But before we do ask those questions, I still want to see a map. What does the water table look like if I could see it from space, for example? And we don't have a lot of data. So the natural thing to do is to fill the data gaps with a process-based model. So we just coded up that conceptual model as I described earlier and run it on the numerical grid. Then we have the problem. We don't really know what is the permeability porosity on continental global scales. And we know that generally porosity, permeability decreases with depth. So we just have to let us get away with this simple assumption that permeability decreases exponentially from some known value that we can glean from the soil data. To inject some reality, we let this exponential decay rate vary by terrain slope, so that on very steep slopes, the regolith is thin, And we can let the decay go faster. And in the river, in the large flat sedimentary basins, we have a lot of sediment. We can let it go slower. So that's the best thing we can do at this point. I'll come back to this later. And then solving that equation is basically to push Forsheimer to the vertically integrated flow at a very high resolution, globally speaking, at 1 kilometer scale, and use some kind of climate where large-scale model constrain the recharge, and with sea level boundary condition, we get this map. A lot of things are wrong, and of course they're wrong. We don't have real geology. And we don't have actually, where it's shallow, we don't have vegetation using the groundwater. And if they do, they will bring the water table down. Of course, there are a lot of problems here. But I'm after the patterns and ask those very, very simple questions. Are there enough shallow groundwater areas to make it relevant to global processes? And are they decoupled from climate? So I want to zoom in a little bit to see, in the earlier map, you see that here we show it's all very deep, and which is really not true. And if I zoom in, you can see at the kilometer scale, a lot of the shallow perched aquifers in the river valleys. And here is Pilot Valley. I did my dissertation under Chris Duffy, and our trucks often get stuck there. It's very wet. I know, so that I know this is real. And so what did we, through this little exercise, what did we learn? And shallow groundwater is quite prevalent on the global scales. And we see, just like the conceptual model, there's some level of decoupling. And if you look at the water table simulation, the model has an exponential shape. And this highest bar is where water table keeps popping off, out of the surface, seeping out to supply rivers and lakes. And the observations has a more of a different shape, and because the observations are groundwater monitoring wells for water resources, and they don't really sample those big swamps like Western Siberia and Boreal, and they don't really sample where the deserts are. And so we have some observational bias, but you know, it's reasonable to expect exponential distribution just because of topography. I have this distribution. So then the next question is, if there are prevalent shallow groundwater and there's some level of decoupling from rainfall, then does groundwater mount to a global driving force to explain critical zone patterns and processes? So that's my second question. How does influence CZ at large scales? I'm going to use 4 examples. The first, wetlands. And here are mapped wetlands. And here are the water table simulations. Despite the fact that we destroyed half the wetlands, especially in this area, you see a very striking correspondence. And when we take groundwater away to simulate the land surface wetness, and we get bone-dry soil because those are coastal plains, that sandy soil that drains very quickly without the groundwater, the bottom of the drainage. And the fact that they are really sea level limited drainage. You can't just drain. Doesn't matter how permeable your soil is, it cannot drain. And sea level control is critical in understanding global change. And over glacial, interglacial timescales, the sea level has gone up and down more than 100 meters. And so it's a moving target. And the groundwater land drainage, the rivers down-cutted, the groundwater seeped out, as described beautifully in this paper called Coastal Oases, Ice Age Springs and Emerged Continental Shelves. And with all these emerged continental shelves, that's how groundwater followed the sea level and formed extensive coastal wetlands. And they are the basis to explain when and how early humans migrated out of the continents, because they are fertile land with water, and vegetation follow the water, and animals follow the water. Early humans are hunters and gatherers, and they followed animals. Same story as in Beringia. And they are holed up here for 26,000 years before they actually crossed to North America because of this ice-free, water-rich lowlands. And besides, wetlands, especially water table depths, are critical in explaining methane cycle in the past 400,000 years, shown in here. And we know that methane fluxes are really dominated by natural wetlands. And so we try to reconstruct the LGM, the large glacial maximum wetlands, using those GCM models doesn't have groundwater, and we can't even agree on the direction of change. Are there more wetlands during the last glacial maximum or less? And wetlands are really drainage features, but not climate features. So without really constraining the drainage, we have a hard time understanding the methane cycle. And this decoupling of wetlands and climate is also shown here. This is some of the driest spots on Earth. And on the ground, this is what it looks like. And so we know that the marsh Arabs have lived here for thousands of years and built extensive culture with the reeds. And in the Sud, another very dry place in the Sahel, and this is known as the Great White Wild Swamp. And on the ground, this is what it looks like. And so it's groundwater prevention of drainage that keeps this area wet. And the early travelers described this as formidable navigation barriers because those large floating mats. But they are actually homes of villages, of towns and villages. And further north, on the edge of the Sahara, there are these groundwater-fed oases, and they harbor reeds, which are really aquatic plants, and palms. They're really out of place. They don't really belong here because they belong to the past. And 6,000 years ago, we know the summer monsoon was stronger, and so the tropics were wetter. And we know that using a GFDL model simulated 6,000 years ago climate, we drive our water table model, and here is how the wetland in the Sahel has expanded. And so when the climate got drier, they shrank and became isolated pockets. And these are really important because these stable, isolated pockets are nature's botanical garden seed banks, what we call evolutionary refugia. And the stable environment allowed species to survive. And then when the climate went back to the more favorable habitat again, and they recolonize, and these micro-refugia are a theoretical necessity to explain today's biogeography, species distribution, etc. And because it has implications for conservation, for identifying hotspots of biodiversity and preservation, and a lot of research on refugia have come, and the number of publications have increased exponentially. But the necessary condition for a spot to be an evolutionary refugia is that it has some degree of decoupling from regional climate. And those isolated groundwater seeps are precisely that. My second example is the Amazon dry season ET. Amazon gets a lot of rain, but for several months there is very little rain when the radiation picks up. And with land models that are fed by rain only, and of course this is a NASA GISS model simulation, you have a steep decline of evapotranspiration that follows the rain pretty much. And observation-based studies show it didn't change much and actually picks up a little bit. There are a lot of explanations for this. The theories are that the soil are just too shallow in the models, and the roots actually go far deeper, and there's hydraulic redistribution to buffer the dry season. But as a hydrologist, we know that groundwater has a seasonal buffering effect. So naturally, I would want to know if groundwater played a role here. And I dug up some studies. This is all I could find. And the blue is in the valleys, the red is on the hilltops. And the water table range is deepest 12 meters. And this paper, 1994 paper in Nature, dug a soil pit and found roots in 18 meter deep. So putting all this together, groundwater has to be relevant. And there are groundwater can be direct source through capillary flux, etc. But I'm going to talk about the two hill slope scale processes that we are familiar with that are critical for explaining this apparent less of a water stress. And so before I go there, here we did a first data model simulation and look at the central Amazon. You have a lot of shallow groundwater, blue, and white is where actually groundwater bubbles out. And in the Cerrado region, you see the same. In the valleys, you have groundwater bubbling out, and these are really reported hotspots for CO2 outgassing. And so I want to talk about just two mechanisms. One is impeded drainage. If the water table is that shallow, then it just doesn't drain. And so I run two models, one with just fixed soil depth and 4 meter long, and let rain drain freely and some use by vegetation. And then the other model with groundwater level rising and falling, and some will prevent drainage in the low ground. And so I want to see what difference it makes. The point is that if we let it drain so quickly in the wet season, then beginning of the dry season, there is not much water left. So we need to see how it changes the wet season drainage. And so this is a model with groundwater on the top and without groundwater, and this is the difference. So the difference of water lost at the end of the wet season. And the difference is huge. And on the average, it was 2 millimeters a day. And that is on the order of dry season ET, actually. And then where the water table is shallow, and you have the greatest difference. Of course, the shallow groundwater is preventing drainage. And so this impeded drainage effect due to groundwater implies much less water loss in the wet season, a stronger start at the beginning of the dry season, hydrologic common sense. And another one is the hill slope flow and the sustained delivery, the lagging, the slow motion, and then so that the outer phase of water table height with the rainfall. And so the valleys are always wet because of the long-term sustained delivery. And so we can look at this model result here. This is groundwater, and this is soil moisture. This is evapotranspiration. In the peak wet season, here's the peak dry season over this box. And water table wet and high, and then dropped in the dry season. And soil moisture wetter and drier in the dry season. Those patches of the soil texture, the sandy soil, stand out. And in the wet season, ET has nothing to do with soil moisture because this is a radiation-limited process. But in the peak dry season, the valleys transpired at potential rate. And so this time delay really creates a spatial mosaic that keeps the valleys perennially wet, which sustain those gallery forests that are common features of the ecotone of all tropical rainforests and tropical savanna. So again, those are the hill slope processes. And then if you capture them in the model, and they can affect large-scale fluxes. And then if we do a coupled simulation of groundwater, soil moisture, and the flooding height, and then here is Grace measure total terrestrial storage, and we really realize that groundwater really is the anchor. And its rise and fall is regulating the soil moisture to a great extent and regulating flooding and also total terrestrial storage. The groundwater rise and fall explains about 70% of Grace observed. So when we put this together, we let the system evolve together, just driven by gravity, nothing else. And we can make a lot of sense. We just put in our hydrologic common sense. We have a far higher ET. It's a lot easier to explain the terrestrial water storage change. Okay, my third example is plant rooting depth. If water table with groundwater is to affect our land ecosystems, it has to be through the roots. And so how much use groundwater is to plants will depend on how deep the water table is. But then how deep the water table is will depend also, how much the water is useful for the plant depends on how deep the root will go, right? How deep the root will go will also depend on groundwater. Is it a potential source to pull the roots down, or is it too shallow to push the roots up? And so on the other hand, if the roots are using groundwater, then can really draw the water table down and do roots follow? Or does it affect root uptake by other plants further downstream? So these are the chicken-egg problems, but there's some things we can say. There's some simple patterns I think we can generalize. So along this groundwater gradient, and this gradient can be scale invariant, regional gradient or local gradient. And there are those high spots that are completely decoupled from the groundwater. It will affect the recharge, but it will not be affected by groundwater. Rooting depth will be just tracking the rain penetration. And further down the gradient, and the plants are likely to use rainwater. Of course, it's just easier. Plants are lazy when there's water in the surface. And they only use deep water when they have to. And so this will result in this so-called dimorphic roots, which is often observed, like this example. This is the eucalyptus tree in Western Australia. And you have this dense cluster on the top, and then those deep sinker roots going through this massive laterite and reach the groundwater at 14.9 meter, and then branches sidewards. And then further down, you have pretty much optimal conditions for roots. So roots are not really limited by water, and they're happy to do something else, maybe searching for nutrients, etc. And then further down, you have different problems. Here, the groundwater is not a blessing, and instead it's a curse because it deprives oxygen. And so it causes anoxia and also salinity in arid regions, as well as lots of toxins, aluminum, etc. So roots try to avoid them, so roots get pushed up. And so these are what we see commonly. If you hike in swampy forests, you often see those very shallow and extensive root plays. Those are common sites. And so if water table can have some regulatory effect on the rooting depth, and I want to see how they distribute. Do they follow groundwater? And I start looking at some early global synthesis by Rob Jackson's group. And so he plotted here the rooting depth, and then rooting depth, different species by the biome. And there are huge ranges. And there are very little pattern. Of course, the soil, the species, the age, the growth form all play a role. But perhaps topographic position or drainage also played a role. But unfortunately, this data did not record groundwater levels. So I started another data compilation, and in about 2 years, I came up with 1,022 data points. And they plotted, they don't amount to much on the global map because they're on top of each other. And, but in general, the distribution is mostly roots are within the 5 meter, but there are those quirky ones that goes all the way to the 17 meter. And the shallowest in the boreal and the desert, and then deepest in the Kalahari, and which is over 70 meter, and here is less than 10 centimeter, about 7 centimeters, so 2 orders of magnitude, no, 3 orders of magnitude difference. And so I recorded groundwater wherever the report gave me that value. And so I plotted on this vertical axis rooting depth versus rainfall. And if they reported rainfall, some of them reported rainfall. And you see all these lines that are the same rainfall but very different rooting depth. This is often the case. Each report has a very small area, but they sample different topographic positions and different species. There's a lot of huge variability at any given rainfall. But if you plot the rooting depth versus the water table depth, the data seems to collapse better, and they are either pulled down toward the water table. These are roots above the water table to tap that groundwater resource. Where they are pushed up by the water table because of the oxygen barrier and the salinity barrier. And some of the roots went below the water table because the water table rise and fall, and the roots lag behind that, and then also temporary tolerance. And so I looked at a subset of the data. This subset data come from this little book called The Tree Root Systems in Eastern Nebraska. About 60 trees were excavated in the Great Depression to provide jobs for the unemployed. And the boxes of data were just lost. And then nearly 50 years later, they were discovered and they were published. And they are full of pages and pages of beautiful drawings. And here, Plains cottonwood, same species, water table 2.5 feet, water table 16 feet. And you see the roots being pushed up or pulled down, and then roots branch out. And just pages after pages of those examples. And then here is Siberian elm, same age, and the water table 6.5 feet, and here is 16 feet. And again, examples after examples of groundwater control. And so I plotted all the data on this graph again. I have rooting depth and water table depth, and the data fall into three clusters. Here, the roots are groundwater too deep, deeper than 30 meters. They just couldn't bother. And here you have roots that are pulled closer to the groundwater, and that taps the capillary rise. And here you have roots restricted by the groundwater. And the climate really doesn't matter. This is the power of this little data set. Climate is doesn't vary too much in this over small area. And the soil, inevitably, silty loam, different kind of silty loam. And so the signal of groundwater was brought out more clearly. So maybe we can have a new conceptual model that use groundwater as an independent, we know it's decoupled with the climate. We know it varies a lot under the same climate. Maybe we can use that as an axis, as a drainage axis versus the climate axis. You have low arid rainfall in pulses and the seasonal rainfall and the per-humid. And then you have groundwater, very shallow, poor drainage, and to very good drainage. And water can come in from the top. Rainfall penetration has a depth, and groundwater capillary rise can have another source. And there's a dry gap. This dry gap will decrease as we get more rainfall penetration or shallower groundwater. And at some point, the roots can penetrate it. And so we see the observation shows that the shallowest roots as well as the deepest roots are in the desert region. And this polarizing behavior of roots really reflecting the polarizing water regime. This is what Oscar Meinzer, the father of groundwater hydrology, wrote in this beautiful prose, plants as indicators of groundwater. In his first sentence, he says, perhaps the most outstanding feature of the flora of the desert is its relation or lack of relation to the water table. And Austin Kamen, the pioneer of root studies, said there may be a very intimate relation between the occurrence of certain species of trees and the character of their roots, having regard to the depth at which perennial water may be found. And so if groundwater can be a almost orthogonal axis to explain rooting patterns, then we have a whole bunch of questions that follow. How deep are roots anyway? Our Earth system models assume 2 to 3 meters with woody species and 1 meter with herbaceous species. And probably not so. It probably varies greatly, and by climate, by species, as well as by groundwater. So on the top is the rain, on the bottom is the groundwater. How do these two regulate? How do their seasonal, how do face nature regulate the rooting depth? And that leads to the question, how deep is the soil, which is defined by biologically activated layer? And so roots are really pioneers for the biological activities. As the roots got deeper, they invited other microbes, other friends and enemies and consumers and decomposers. They all follow. So I think we probably should really think about these questions and ask those questions. How deep are roots anyway? It has a lot of implications on carbon cycle, carbon storage, weathering, soil development. Okay, my last example is continental weathering. This is work done by Catherine Moore at Stanford. So we have some major carbon events in the Earth's history. Here's 600 million years. This plotted here is the partial CO2, relative CO2 to today. Today is 1. And it was 20 times higher at 600 million years ago. And there was a steep drop. And this steep drop was related to roots. Plant roots developed from Silurian to Devonian. No roots found in the fossil soil, a lot of roots, deep roots and large statured trees in forest valleys. And the development of vascular plants and the huge consumption of CO2 pulled in the CO2, cold atmosphere, and the biologically enhanced weathering, all that carbonic acid by roots and by microbes also enhanced the chemical weathering. So this major event is critical zone event. And that brought Earth into the Permian Ice Age. And then there's another cooling event, the late Cenozoic event, that brought Earth out of the hothouse, the Paleocene-Eocene thermal maximum, the PETM, and into today's glacial interglacial oscillation. So Catherine's work is relating to late Cenozoic. So how do we explain this one? The roots have already established, so plants is not the reason. So this paper, probably one of the most cited papers by Reinfelder and Rutgers, said that it's a tectonic force in cooling lake Cenozoic. So the uplift and the rise of the Himalayas exposed fresh water, fresh rocks to enhance orographic rainfall, that enhanced the weathering. But then people said, critics mostly say, how can Earth cool without plunging into a deep freeze because the mountains are still uprising? And so there are a lot of explanations, of course. As cooler, the chemical processes slow down, and there's a lot of negative feedbacks. But one key negative feedback is the hydrologic regulation of chemical weathering and the geologic carbon cycle. So the theory is very simple, and it's the preferential flow and short residence time of groundwater and the short interaction of rock and water interaction time. And so, so the water coming out of the newly uplifted terrain is very diluted. It's far from chemical equilibrium, which is a very effective bottleneck in slowing down weathering. And if you look at her citations, here is Jim Kirchner, another paper, Jim Kirchner, Ronaldo and Morani and a lot of Jeff McDonald. They're all hydrologic publications, and the journals are WRR hydrologic processes and non-faking transport models and reactive transport models. So basically we know this all along, but it takes someone to ask the large question and to really demonstrate to us that what we do, what we learn at the CZO scales, what we measure, we observe, we try to interpret, are directly relevant, are equally essential to global scale processes. So those are my 4 examples just to show that what we do at the CZO scale can scale up, and they are equally essential in interpreting global scale processes. So then looking forward, what should we do? How can we communicate what we learn at the CZO scale to the Earth system modeling? How can we link, how can we help the Earth system modeling community to improve the hydrologic presentation? I think it's imperative we ask this question. Earth system models are here to stay. Earth system models are here to stay. And they are the best tools for us to really get some idea on what possibly could happen in the future. And by doing this, both communities benefit. And we bridge this gap between the scale of observation and conceptualization and intuition with the scale that we have to make predictions. And we bridge the observers and the modelers, and we bridge our CZO scientists with Earth system modeling scientists. And so I think there is tremendous benefit to be gained if we make an effort to contribute our collective wisdom from this community and communicate that. And there are many things we can do, of course, and I think some obvious things is community modeling. Many things I'm going to list, but one top on the list is community modeling. We don't have the institutions and the culture to develop community models that are focused on large scale and water flow in this critical zone. And a lot of this work has started, and NASA has funded CUAHSI to organize 3 workshops that Jay led. And then one of the conclusions is that it's time we focus on large-scale continental models. And this model will be our laboratory for us to test our hypothesis. What we learn at with the CZO scales can actually survive the successive zooming out and still show up on the continental scales. And we can learn so much by this model. And the second thing, I'm sorry, that's right, if I move on, but how do we do this? How do we develop a community large-scale hydrological model? There's a lot to be discussed. There are many, many paths. For example, I really think that we must capture the CZO scale processes. And hill slope, we cannot go below the fundamental first-order stream hill slopes. We can grow a continental model from what we know. On the other hand, I also think it's critical that we can start from existing community models already used in Earth system models and put what we know into it. So what is the best path? Or maybe we can go together. These are some of the issues we will discuss today. Some of the sessions of the meeting will be devoted to discuss this today. This is a community effort, so we really have to agree upon what's the best way to go forward. And then the second thing is synthesis. And we need to put all our model and data together, make sense of large-scale changes. And synthesis and the reconstruction of past changes lies in the heart of all Earth scientists. And we look at those ice cores, ocean sediment cores, we can really test model and ideas and with data and explain what happened. And all these different proxies, we need to put it together. One question we can ask is, what really happened to the U.S. water cycle change over the last 100 years? Can we explain the observed stream flow changes, stream chemistry, stream temperature, and all the data? Can we put all this data together and use a continent scale model that span the range of hill slope to continent? Can we make sense? And what part is caused by humans? What part is caused by natural variability and trends? So there are so many questions, so much we can learn. So I consider this synthesis project really a teaching lab for us to figure out what has happened. And we don't have data in the future. The past is the way we learn. And then that comes data support. We have to have data. If we do continental model, we need continental data. And here is the water data center will play a critical role, I see, to put together a graded continental database. Another effort we have started is something called digital crust. That is, we want to have continent scale permeability, porosity, go below the soil depth. And so this digital crust effort has kick-started and with the USGS Paul Center funding and with also NSF EarthCube funding. So we're dreaming, in a nutshell, a four-dimensional integrated data system of crustal composition properties from land surface to the brittle ductile transition, where we know that the convection is negligible. So we are talking about a geological scaffolding. People will ask me, why don't we just focus on hydrogeology, put in the aquifers? But we don't always have aquifer data, top test data, and the geology is the fabric, is architecture of hydrogeology. So we need to really reach out to other solid earth scientists to build this digital crust. And through Paul Synthesis Center, and we reach out to USGS, and Sky Bristol is the Chief of Applied Earth System Informatics Research, and in collaboration with Steve Richard of Arizona Geological Survey, he runs the USGIN, the Geoscience Information Network, and the geothermal database of the nation. And Shannon Peters, who have built this macro strat, which he put together all the stratigraphy data. And he's a paleontologist, and when he put this data together, you can click any polygon and see the entire sequence of lithology, mineralogy, and the depth and the time and the age of rocks. And so, through putting this data together, Shannon came up with wonderful stories explaining the mass extinction event. And so this kind of synthesis projects and data integration projects are very rewarding. And then also in collaboration with Ilya at San Diego, who has been a friend of CUAHSI, and he has this Brain Atlas project, which is similar to the Earth, 3D system with a different kind of data, all formats, all data, great resolutions, etc. And Niels Musdorf from University of Hamburg, he has put together this global lithological method for really understanding weathering projects. And if we have global groundwater models, now we can really couple with this and to really understand what is the flux of chemicals into the ocean. But this is 2D, so we're working together to build this three-dimensional database. And the foremost CUAHSI. CUAHSI has been the leaders of this digital crust, which has cross-cutting implications to other Earth scientists. And here's Jennifer organized a NSF EarthCube working shop to gather community input. And Rick is Paul Center working group member, and we are heavily involved in the development of the concept. And here's a picture of Rick demonstrating the upper crust with a delicious edible model. And so in a nutshell, we're dreaming a 4D or 3D Google Earth. We're reaching out to Google so that not only you can zoom into a spot, but you can dive down and you can see what's below land surface, crossing the folds and the faults, and there will be a lot of fun. So, but this is a very, very ambitious project. So EarthCube has funded us only half of the money we requested to get it started. So in a year from now, I may have something to show here. And lastly, we need to really reach out to the Earth system modeling community, particularly NCAR. NCAR has established institution, culture, and experience in growing community models. Sorry, I went a little too fast. And some initial discussions have started with NCAR through David Gotches, who cannot be with us today, but Dave has always been a bridge between our community and NCAR. And then Martin Clark is with us today, and I look forward to discussions. And Dave Lawrence also leadership of the NCAR Climate Land Community Working Group. So I think we really need to work together. Both communities have a great deal to learn. Finally, I want to honor Peter Eagleson by this little story. When I arrived in MIT in 1993, Peter Eagleson had just retired, but occasionally come to the group meetings. And one of the meetings, Fatih presented the Amazon precipitation recycling work, which has now become a classic. And Peter Eagleson leaned back and said, how deep are the roots? Of course, nobody had the answer. Everybody scratched their head. 2 meters, 3 meters, that's what the model tells us. And I took a mental note, and I said, when I grow up, I'm going to look into that. 20 years later, we know it really, really varies. Amazon is huge, and the drainage must be a factor. On the terra firma forest, this is in Tapajós National Park, and the high ground, the water table is at least 20 to 30 meters deep. And the roots can be probably quite deep. And here is that, again, that 1994 Nature paper put a data point, 18 meters, at least 18. That's the pit they dug. It could be much deeper. But then in the swampy forest, and nobody has excavated. It's too wet. Why would it do that? There's no water limitation, right? So there's no data. I'm still searching for some excavation in the swamp. So they have to actually take the water away to see this. But we have some notion, because by looking at the above ground, those huge buttresses must be there to compensate for the lack of anchorage because of shallow root. And we do know that the size and frequency of buttresses decrease with elevation or improve the drainage. And so when I finish my data compilation, I'm only gone through 20% of data literature I found, and I'm going to send paper to him. And with my last slide, I have to confess that after I prepared for this talk and I went back to read this article, The Emergence of Global Scale Hydrology, and I kicked myself. Everything I said today has been said far more eloquently and convincingly nearly 30 years ago. And when I read this paper in the 90s, I just didn't get it. And I do now, I think. Thank you. That's all. I probably ran over, right?
No, you did great. Go ahead and call on anybody else.
Maybe we can have our break, and then we can talk later.
First of all, let me say that I am very impressed, and congratulations on this very exciting talk. And I have a very specific question on the past pattern of CO2 concentration. And you said that you think that there is a relationship with vegetation activity. And don't you think that it could be also dominated by the CO2 emissions by the oceans? Because if in the past we had an increase of temperature, then this provokes an increase of CO2 emissions from the oceans, and this could prevail on the vegetation activity. What is your view on this?
Are you talking about the Silurian, Devonian transition, or the Cenozoic transition?
Yes, yes.
The Cenozoic?
Yes.
Yeah, and there are many, many explanations. And my colleague Dennis Kent said it's really not the uplift mountains. It's really the Indian subcontinent crossing the equator, and paleogeography explained this. Crossing the equator, the Indian subcontinent was all silicated volcanic rocks, and crossing the equator with all that rain that actually enhanced the weathering, pulled the CO2 in. And then there's other explanations. Grassland. Grasslands are more recent ecosystems. The grasslands are known to have extensive roots to pull in CO2. So there are many, many explanations. But I really think that the Raymond and Roddiman paper still is probably considered the consensus is the most likely case.
Ying, that was a wonderful talk. Thank you very much.
Thank you.
A question on the impacts of irrigated agriculture on some of your modeling.
Right.
We've sort of moved the water table from hundreds of meters deep now back to the surface in large areas. What you want to just philosophize a bit on what impacts that may have, or are we starting to model that at all?
Yes, there are a lot of studies have done. If you go through a literature search, you'll find hundreds of papers. And so what my group did was to look at the coast water cycle. When you pump groundwater out, especially Ogallala aquifers, you definitely enhance ET. That's the whole idea. Growing plants to enhance ET. And that ET will be transported down and then rain out somewhere. And we know the low-level jet goes through the Midwest. And we know the dust bowl era, when the dust picked up on the high plains, it deposited in Chicago, in Washington, D.C. So that gives us a tracer. We know something happens in the high plains will impact the downstream. So what we found is that by taking the groundwater, depleting the river flow from the left side, from the western side of the Mississippi, we actually put more water on the eastern side of the Mississippi. So there are lots of different stories, and then, it's a very rich literature. But I have to say that a lot of GCM studies on irrigation impact on the climate, we have a hard time constraining how much irrigated water do we use, and how wet the land should be, and it makes a big difference. If you specify irrigation as field capacity versus saturation, you have a huge ET effect and downwind effect, of course. And that shouldn't be arbitrary, in my opinion. If our model had actually groundwater integrated part of the water cycle, then we can, by looking at river decrease, and we know how much groundwater is pumped, we can really make a consistent water budget, and so we can constrain how much irrigation water is used and how much impact on the climate. So the whole cycle needs to be considered together in those large-scale models.
I have a question. It's right slide now. I'm asking about your feeling. You're doing science, and you have to ask for money all the time.
Yeah.
On the slide, you said you were graduate student or whoever, postdoc, and you cannot understand something. And now you ask for money, what people don't understand a lot of what you're doing. So what is your feeling? What do you need to ask for money? Thank you.
It's a sensitive issue. Funding is hard, let's face it. That's why I'm doing the work myself. I'm cheap. I'm actually free. So I collect the data myself, and it's my evening job. And I actually enjoy it. I get a feel. I read a paper. I go to Google Earth, and I take a virtual field trip. I love it. And so I'm not complaining. I don't have a single student now. And my last postdoc graduate, I have no funding. So I'm not worried about that because I'm having fun. I want to have the fun to myself, All right. Thank you. You're welcome.